Ever wondered how machine learning can predict almost anything with enough data? Well, I know I wanted to. It can be hard to learn something new. You don't know how to start or where to look. Well, I promise you, this video is the perfect starting point. You will learn the basics of machine learning, and before you know it, you'll be making your first real machine learning project. So keep watching until the end to discover the beauty of linear regression and all the amazing things it can be used for. That said, let's begin. We'll break down the fundamental components using the parameters m, x, y, and the hypothesis function h of theta. Our goal is to make accurate predictions based on this model. This is done by the hypothesis. For simplicity, we will start by looking how a linear regression model with one variable looks like. This might remind you of following classical formula. In both equations, y or h of x is our prediction. X is the input variable or feature. Theta 0 or b represents the y-intercept, the value when x is 0. And theta 1 or m is the slope coefficient, indicating how y changes for a unit change in x. During training of the learning algorithm, our goal is to find good values for the parameters theta to make accurate predictions. How this is done will be explained later on. If you want to understand the difference between regression and classification problems or need a refresher on regression problems, you can check out this video. That said, let's understand the critical parameters we're dealing with in linear regression. Let's do this with following example. Assume we have a regression problem that tries to estimate the amount of horsepower a car has based on the price of the car. Then our dataset might look like this. From now on, we will call this the training set because it is the data on which the learning algorithm will learn. M is the number of training examples we have. For example, if we assume the training set has 29 data points, then M is equal to 29. Next we have X, which are the input variables or features that we're using to make predictions. In our case, X consists of only one feature, namely the amount of horsepower. Later on we will see regression problems with multiple features. We also have Y, which is the output variable or target variable we want to predict. If we want to talk about a specific training example, we will denote it with a superscript. If we want to talk about the ith training example, we will use this notation. To get familiar with this, let's look at some examples. Lastly, we have our hypothesis function, which maps x to y. It's our learning algorithm, and for linear regression, it takes this form. It's essentially the equation that represents our linear regression model. H of x is our prediction, the estimated value of y based on the input x and our model parameters. Theta 0 is the intercept or bias term. It represents the value of y when x is 0. Theta 1 is the slope coefficient. It tells us how much y changes for a unit change in x. Our goal is to find the best fitting line, which is our hypothesis function, that represents the relationship between x and y. Now, here comes the exciting part. During training, we adjust the parameters theta 0 and theta 1 to make our hypothesis function as accurate as possible in predicting y based on the given x values. In future videos, we'll explore how to train the model, find those optimal theta values, and interpret the results. Now we're going to explore the cost function of a linear regression model with one variable. Remember the training set that we saw in the previous video. Here we learned that the hypothesis for linear regression with one variable looks like this. With theta 0 and theta 1, the parameters of the hypothesis and x being the input variable. What we haven't seen yet is how we can choose these parameters. What should the value of these parameters be? Or in other words, what line will fit best through our data? That's what we will see in this video. First, let's recap what will happen to our hypothesis if we change the parameters theta 0 and theta 1. Let's look at these three examples. In the first example, we set theta 0 equal to 0 and theta 1 equal to 1. This will result in the following hypothesis. In the second example, we make theta 0 equal to 1 and theta 1 equal to 0.5. And lastly, we show an example where theta 0 is equal to 1 and theta 1 is equal to 0. So now to come back to our question. How can we choose values for theta 0 and theta 1 to get the best fitting line through our dataset? Well, the idea is to choose the values for the parameters so that our hypothesis is close to the real value, y, of the training examples. In many cases, there is still an error between the predicted value and the real value. So the goal is to minimize the error between the hypothesis and the real value of the training examples, as this will guide us to good values for theta 0 and theta 1. We will express this minimalization problem with a formula. We want to minimize the total error of all training examples. This is done by taking the sum of every error between the value of the hypothesis and the real value of y. We want to sum over the entire training set, so we sum from 1 up to m, which is the total amount of training examples. Note that we only want positive errors so that we can sum them up. For this reason we will square the error. Further, we also add a term 1 over m to take the average error. And we add a term 1 over 2, which is just a constant to make the upcoming math a little bit easier. This term that we just wrote down is also called the cost function for linear regression with one variable and is denoted as j. This specific cost function is also called the squared error function, and even though there are different cost functions we can use for these linear regression problems, the squared error function is the most used. So to recap our goal. Our goal is to find the best values for theta 0 and theta 1 by minimizing the cost function which is dependent on theta 0 and theta 1. To illustrate what this cost function means, we will look to an example where we simplify the hypothesis by setting theta 0 equal to 0. In this case we will try to find the best value for theta 1 and our hypothesis will be simplified to theta 1 times x. If we look at these data points on the graph, we see we get the following training set, with 3 training samples. The first training sample will be data point that has x equal to 1 and y equal to 1. The second data point contains x equal to 2 and y equal to 2, and the third and last training sample is 3, 3. Remember that we use the notation superscript 1 to denote the first training sample, superscript 2 to denote the second training example, and so on. Now to see what it means to minimize the cost function, we will look to 3 different values for theta 1. For the first one, we assume that theta 1 is equal to 1. Then we get a hypothesis that looks like this. Next, we can calculate the cost function. As there are 3 training examples in our training set, m is equal to 3, so we can plug 3 into the equation. Next, we can calculate the 3 errors between our hypothesis and the y value of our training examples. The first training example has x equal to 1 and y equal to 1. If we plug this x value in our hypothesis we get an estimated value of 1 times 1. So h of x with x equal to 1 is 1 and y is 1. So, we get 1 minus 1. Next we can do the same for the second and third training example, which will give us 2 minus 2 and 3 minus 3. If we calculate the value of the cost function for theta 1 equal to 1, we find a value of 0. Now let's see what the value of our cost function becomes if we choose theta 1 equal to 0.5. Our hypothesis will now look like this. Of course the value for m and the values for y superscript 1, superscript 2 and superscript 3 will stay the same as we are still working on the same training set. Only the value of the hypothesis will change, and this again illustrates that the cost function is only dependent on theta 1 and theta 0. Only these parameters will vary, they are the dependent variables of j, all the other parts will stay the same. We can now calculate what the hypothesis predicts if we give it as input x superscript 1, which is 1. This will give us 1 times 0.5, which is just 0.5. We can do the same if we give the hypothesis as input x superscript 2, which will result in 2 times 0.5, and we can also give the hypothesis as input x superscript 3, which will be 3 times 0.5. Now we get a value of 0.58, which is different from 0. Before we look into what this means, we first calculate the value of the cost function for one more value of theta 1. Now we will set theta 1 equal to 1.5. And if we follow the same principle as the last two examples, we will also get a value of 0.58. We can now look what it means to minimize a cost function. But before we do so, please consider subscribing, as this will really motivate me to make better videos and so you never miss a new video. That said, let's now plot these different values we just calculated in a graph. We can plot the values of j in function of theta 1. For the first hypothesis, which is indicated with the blue line and which had theta 1 equal to 1, we got a value of 0. For the second hypothesis, indicated with a yellow line and a theta 1 of 0.5, we got a value of 0.58, and lastly for the third hypothesis, indicated by the red line and a theta 1 of 1.5, we also got a value of 0.58. So, as you can see, for every different value of theta 1, we get a different hypothesis and thus a different line through the data. In fact, if we would calculate all the possible values for theta 1, we get a continuous function of theta 1. This continuous function is called the cost function, and it can tell us which value for the parameters, which in this case is just theta 1, because remember, we simplified the hypothesis by putting theta 0 to 0. It can tell us which parameter values will give us the hypothesis that fits best through the data. All we have to do is to minimize this cost function, or in other words, find the minima of this function. For this example, it is quite clear that 1 is the optimal value for theta 1, as it will give a cost of 0. Or in other words, the predicted value by the hypothesis is the same as the correct answers in the training set. Or in other words, h will be equal to y for all training examples, and thus there is no error between the predicted value and the real value in the training set. Note that this does not mean there will be no error between the trained model and new data points. However, you don't need to worry about this now, we will see this in a later video. I would like to point out the difference between the hypothesis and the cost function. The hypothesis is our model that we want to train. It will try to predict the outcome of unseen input values. For example, what the price of a car will be, given that it has 300 horsepower. It is a function of x, and given a certain input x, it will predict a certain output. The cost function, on the other hand, is a function of the parameters theta 0 and theta 1. It will learn us what the best values for the parameters of our hypothesis will be. It is a very important function in training our model so that our model will be able to make accurate predictions. Now, in the next part we will see what happens if we don't assume that theta 0 is equal to 0. If you look at this graph, it is quite clear that the hypothesis is not optimal for this training set. In other words, there are still pretty big errors between the real value of the training data and the predictions of the hypothesis. To give accurate predictions, we would like to optimize both parameters. In that case, we would be able to get a line through all data points, meaning that the value of the cost function for these parameters is 0. In this case, it would result in the parameters theta 0 and theta 1 both equal to 1. This hypothesis will be way more accurate than the one where we only optimize theta 1. That said, how does our cost function j look if it is dependent on both parameters? This is illustrated in this 3D figure. Like you see here, the cost j is now plotted in function of both theta 1 and theta 0. And this might result in a bowl-like figure like you can see over here. The cost is now depicted by the height of the surface. For example, the value of the cost function at the points theta 0 equal to -5 and theta 1 equal to -5 will result in a cost of around 50. And as we can see, this is a very high cost in this figure. We now can conclude it is a pretty bad hypothesis for our dataset. As you can see, the minimum of our cost function will lay somewhere around the point theta 0 and theta 1 equal to 0. However, we can illustrate this 3D cost function into a 2D figure, also known as a contour plot. This will make it easier to illustrate how we can minimize this cost function. If you don't know contour plots, it looks like this. It is used to represent the 3D figure in 2D by making use of contours of different colors. These different contours represent in this case the height of the cost function. All points on the same ellipse will have the same value for j, so this point will have the same value for j as this point. Now we can also see the minimum of the cost function more clear. We can now read our minimum as the center point of the lowest ellipse, which gives 0, 0 in this case. If we now look back at our previous training set, where we had these data points, we can look at an example of an hypothesis. If we look at this hypothesis where theta 0 is equal to 2.07 and theta 1 is equal to 0.5, we can search for this point on our contour plot. If we search for both values of theta, we find this point. It is clear that this is not the optimal hypothesis. There are still a lot more combinations of theta 0 and theta 1 that give a better hypothesis. In fact, all the combinations between this ellipse will give a better hypothesis as the value of j will be smaller. Previously we saw that the optimal values for theta 1 and theta 0 were both 1, and indeed if we look at the contour plot, this is true. And if we indeed set the parameters of theta 0 and theta 1 equal to 1, we get the following hypothesis. This is an optimal hypothesis. However, we don't want to visually look for the optimal parameters. This wouldn't even be feasible anymore, as we will see in the following videos that the amount of parameters can become really large. We will later see problems with more than 20 parameters, thus also getting theta 2, theta 3 and so on. This will not be possible to plot anymore. So how can we analytically find the best values for theta? Well, we want an efficient algorithm that can calculate the best values for the parameters for us. This can be done with gradient descent. This will be what next video is all about. In this video, we will learn about the gradient descent algorithm that is widely used in machine learning. We'll see what it does, why we need it, how it works, the mathematical formulation behind it, and what this mathematical formulation actually means. So without further ado, let's dive right in. If we look at this cost function, we see there are two local minima. One here and one over here. Now to explain the concept of gradient descent, we will take an initial value for theta 0 and theta 1. We assume this brings us in this point over here. Now, what the algorithm basically does is, it looks 360 degrees around. So it looks in every direction and then it asks itself, if I take a small step in some direction, what direction will give me the steepest decline in the value of j? If we do this, we see that this direction will result in the steepest decline. Now in this next point, where we have different values for theta, we do the exact same thing. We look what direction will have the steepest decline in the cost function. We will keep on repeating this process until we converge in a local minimum. Note, however, that we converge to a local minimum. As you can see on the graph, there are multiple minima, and thus if we start with other initial values of theta, we might end up in another local minimum. For example, if we start over here and we do the exact same process as before, we will end up in this local minimum. This is a property of gradient descent that we will speak about in a moment. But first let's recap what we are doing. In this video we will learn one of the most useful algorithms in machine learning. We will look into gradient descent and how we can use it to minimize cost functions and find the optimal values for theta. We will start by using gradient descent to minimize linear regression problems with one variable, but in fact, gradient descent is a general algorithm and can be used to minimize almost every cost function in machine learning. But we will start with using gradient descent on the cost function we described in the last video. So to recap, our goal is to find the optimal values for theta 0 and theta 1 by minimizing the cost function. Last video, we ended the video by saying we need an algorithm to do this minimization process efficiently, and that's what gradient descent is all about. In fact, this is done as follows. We start with some initial value for theta 0 and theta 1. For example, theta 0 and theta 1 both equal to 0. And then we update the values of theta so that the value of j goes down every step of the way. And we keep on doing this process until the value of j converged into a local minimum. Okay, so now, let's take a look at the mathematical formulation of the gradient descent algorithm. Let's break it down step by step. We'll start with this notation. You might be wondering why we use this notation and not just an equal sign. This is done to be mathematically correct. For example, if you are familiar with programming, you don't have any problems with the expression x is equal to x plus 1. You know that x plus 1 will be put in the variable x, or in other words, we made an increment to the value of x. However, mathematically this is not correct terminology. X can never be equal to x plus 1. So this is why we will use this notation. We will use this notation to say, take the value of x plus some value. For example 0.67, and place this right-hand value in x. So we override x with some new value that is dependent on x itself. So if we look back to the algorithm, we can see that we basically just update the value of theta j with itself minus some term. And we keep on doing this until we converge into a minimum. Now, let us look at what this term means. We'll start with alpha. Alpha is called the learning rate, and it basically tells us how large of a step the algorithm takes. For illustration purposes, let us assume a cost function where theta 0 is set to 0. Then we get a cost function that looks like this, where the cost function is only dependent on theta 1. If we apply gradient descent with a large value for alpha, the algorithm will take big steps like this. On the other hand, if we decrease the value of alpha, the algorithm will take smaller steps towards the local minimum. Now you might think, why wouldn't we take a large value for alpha, as this will be faster due to the fact that we need less iterations? Well, the problem lays in the fact that if you take alpha too large, the algorithm might overshoot the minimum. Meaning that it might fail to converge, or worse, it might even diverge away from the minimum. Like I will now illustrate on this cost function. On the other hand, if you take a value for alpha that is way too small, it will probably take a long time for the algorithm to converge. So ideally we want a value for alpha that is neither too small, nor too large. But to explain the concept of gradient descent, we don't need to know this yet. We will see how to get a good value for alpha in a later video. If you liked the video so far, please consider subscribing so that you never miss a new video, like the one in which we will explain how to choose the right value for alpha. Next, let us look at this second term. If we look closely to this term, we see that it consists of two parts. This first term is called a partial derivative, and the second term is one that we already know. It's the cost function. If you are familiar with calculus, you already know what a partial derivative does. But to explain this, let us look to a simple cost function. Again, if we assume a cost function that is only dependent on theta 1, we can look at a cost function that looks like this. We can now consider two cases. In the first case, we take the initial value for theta 1 over here. Then we try to perform a step in gradient descent. So, what this partial derivative is, it can be represented as the slope that lays tangent to this point on the cost function. So in practice, we use this partial derivative term to look how steep we will decline or incline if we perform a small step in a certain direction. So in this first case, we see that the slope goes down, or in other words, we have a negative slope. If you look back at gradient descent, you can now see that this means that theta 1 will be added with some value, or in other words theta 1 will increase, which is correct if we look back to the graph. The minimum lays to the right of the initial point. We can now also do the same for case 2, where we take an initial value to the right of the minimum. In this case, the slope will be positive, and thus the value of theta j will decrease, and again this is correct, because the minimum lays to the left of the initial point. Now, what do you think happens when your initial theta value is already at the minimum? I recommend that you pause the video for a second and think this through. Well, the answer is, you stay at this minimum and the gradient descent algorithm is finished. This is because the slope will be equal to 0, and thus the updated value will be exactly the same before. So theta 1 will stay theta 1, or in other words, we have converged. Now I would like to point out another important subtlety in the algorithm. For the gradient descent algorithm that we are important that you update all the parameters simultaneous. Meaning that we first calculate all the new values for theta and then update those values simultaneous. This is because the cost function is dependent on all the parameters, and if you would first update one parameters and then the next, the algorithm will follow another path. On the left we see how this is correctly implemented. We first store the new values for theta in a temporary variable, and after you did this, you update the actual variables of theta. Now before we look more in depth how gradient descent looks for linear regression with one variable, we would like to point out one more thing. If you think of a constant value for the learning rate, then you might wonder, how can we ever converge into a minimum? Wouldn't we keep on overshooting the minimum? Well, to explain why this is not the case, let's look back to this example. If the slope becomes 0, we have converged to a local minimum. But if you look closer to this, you can see that when θ1 comes closer to the minimum, the slope gets closer to 0. So if you look what this means in the mathematical formulation, it means that the value of theta gets updated with smaller and smaller increments or decrements when we approach the minimum. What this concretely means is that gradient descent can converge to a local minimum, even with the learning rate fixed. So as we approach the minimum, gradient descent will take automatically smaller steps and we don't need to decrease alpha over time. In the next part we will see how we can use gradient descent, specifically for linear regression with one variable. In this video, we will see what the partial derivatives with respect to θ0 and θ1 are. We will see how the gradient descent algorithm for linear regression with one variable looks like and why gradient descent in linear regression will always converge to the best minimum. But first, let's recap. Remember the hypothesis of linear regression with one variable and its corresponding cost function. To summarize, the hypothesis is a model that predicts a certain output that is called h, given some input that is called x. The goal is to create a model that makes accurate predictions. Or in other words, the goal is to make a hypothesis of which its predictions lay as close as possible to the real y values of the training examples. For example, look at these two models that try to predict something. It is clear that the green hypothesis is better than the red hypothesis, as the green hypothesis will give predictions that lay closer to the real values of the training examples. Or in other words, the sum of squared errors of the green hypothesis is smaller than that of the red hypothesis. So from this graph it is clear that the parameters θ0 and θ1 of the green hypothesis make a better fit through the data than the red hypothesis. However, we would like to find the optimal parameter values with an efficient algorithm, not by graphically reading the values of a graph. To do this, we try to optimize the parameters θ0 and θ1, to get a model that fits the training examples as good as possible. This is done by minimizing the cost function. Remember the cost function, which is basically telling us what the average error between the hypothesis and y value of all training examples is in function of the parameters θ0 and θ1. This optimization process to find the optimal values for theta is done with our beloved gradient descent algorithm. This algorithm minimizes the cost function and only stops if it converged into a local minimum. The gradient descent algorithm looks as follows, with j running up from 0 until the amount of parameters. So in the case of linear regression with one variable, we need to repeat the gradient descent algorithm for j equal to 0 and j equal to 1. As we have seen in the previous video about gradient descent, we will get an algorithm that looks as follows if we try to implement this. We will keep on updating θj, which in this case means θ0 and θ1, so that we reduce the cost function each step of the way, with as goal to eventually end up in the minimum of the cost function. The algorithm keeps on repeating each step until we reach convergence, meaning that the value of θ0 and θ1 stay almost the same as the previous iteration. Or in other words, the updated value for theta is almost the same as the previous value for theta. If you remember from previous video, this will happen if this part becomes near 0, or in other words, if we have an horizontal slope and thus reached a local minimum. So now that we refreshened our knowledge of the gradient descent algorithm, we can look one step further. From the previous video, we know that alpha might be a fixed rate, and how this fixed rate is determined will be seen in a later video. But for now, we will assume this is a constant and focus on the partial derivative term. We saw that this is the tangent line to the cost function, but how do we now calculate this in mathematical terms? For this, let's look closer to this partial derivative. Well, if we calculate the partial derivative of the cost function with respect to theta 0, we get this term. You can see it looks close to the cost function itself, only with the 1/2 gone and the squared symbol gone. I'm not going to explain the entire method of calculating the partial derivative, that's not the goal of this course. But for those that already seen calculus, you can always check this out yourselves. So next, let's see what the partial derivative of the cost function with respect to theta 1 looks like. Again, we can calculate this partial derivative, which will give us the following term. You can see that it looks almost the same as the partial derivative with respect to theta 0, only with the difference that we add the term x superscript I. Now that we know what the partial derivative terms, we can plug them in our gradient descent algorithm. This is the full gradient descent algorithm for linear regression with one variable. And later, we will implement this algorithm in code. If you don't want to miss that, or you like the video so far, please consider subscribing to the channel and give the video a thumbs up. Now, to get some terminology right, this gradient descent algorithm that we just described is also called batch gradient descent. It is called batch because each step of the algorithm, we look to all the training examples. In other words, we sum up the error over all training examples. There also exist variants of gradient descent in which you look to a subset of the training set. This is not something we will see in this video, but it is important to keep in mind. The choice between batch gradient descent and its variants, like mini-batch gradient descent or stochastic gradient descent, often depends on the size of the dataset and the computational resources available. Each variant has its advantages and disadvantages. Now there is one more important thing we want to clarify. Previously we stated that the gradient descent algorithm doesn't account for multiple minima. Meaning that if you choose other initial theta values, you might end up in another local minimum. But the gradient descent algorithm doesn't know there are multiple minima. So you might end up in a local minimum, while there might be a better minimum out there. Like in this example, you end up in this local minimum and the gradient descent algorithm is finished. However, there is another local minimum that is deeper. So it's closer to zero error and thus will result in better values for the parameters theta 0 and theta 1. Luckily for us, the cost function in linear regression will always be bowl-shaped, also called a convex function. A convex function is one where any local minimum is also a global minimum. So for every cost function in linear regression, regardless of the number of parameters, we will always end up in the same and only minimum. This is a fundamental property of linear regression. So for convex functions, the local minimum is also the global minimum, which makes optimization more straightforward. This property is exploited when using optimization algorithms like gradient descent, which is guaranteed to converge to the global minimum for convex functions. Hello and welcome back. Last 4 videos we spoke about linear regression with one variable. Meaning, that we tried to predict something based on one variable or feature. Like for example with this training set, where we tried to make a hypothesis that predicts the price of a car based on the amount of horsepower the car has. So we had one variable, namely the amount of horsepower. For example, if we plot these points on a graph, we get this. Now our goal is to draw a linear line that fits the data best and that will give accurate predictions for new unseen data. So after we trained the model and decided that this is the best hypothesis, we can now try to predict the price given some new unseen data point. For example, we can estimate the price of a car to be around $25,000 given that the amount of horsepower is 83. However, if we think about it, we can give more information than only the amount of horsepower. This extra information will then give us even more accurate predictions. Say for example that you want to predict the price of a car based on the amount of horsepower, the age of the car and the mileage of a car. This gives you way more information about the car than we had before and thus will allow us to make more accurate predicts. But before we will see how this is done, we need to get familiar with some new terminology. First of all, we no longer can just refer the input variables as x. X will now be the entire collection of all variables and we denote the specific variables or features with x subscript 1, x subscript 2 and so on up until x subscript n. Which brings us to a second new notation, namely the letter n, which we will now use to denote the amount of features. In our case n is equal to 3. Also don't forget we used m to denote the amount of training examples, or in other words the amount of rows in our dataset. In our case we didn't define the end of the dataset, but let's say we have 23 training examples, meaning that m is equal to 23. Next, if we try to look to one specific training example, let's say the first training example, then we denote it with x superscript 1. We can express this as an n by one-dimensional vector, namely, this one. And if we want to specify the third variable in the first training example, we denote it by x superscript 1, subscript 3. In our case this will be 7578. So to summarize, we have x subscript j to denote the jth input feature. We have x superscript I to denote the input features of the ith training example, and we have x superscript I, subscript j to denote the value of the jth feature in the ith training example. As we are now familiar with some terminology, let us look how to extend our hypothesis and cost function for multiple features. In fact, as we will see in a moment, this will be really easy. But before we do, if you found this video helpful so far and want to learn everything about machine learning and AI, please consider subscribing. That said, let us look to an hypothesis with 3 input features. As you see, it's nothing more than adding the features x1, x2 and x3 together with its corresponding theta parameters, theta 1, theta 2 and theta 3. There is just one odd thing: we now also add the feature x subscript 0. But what is this? We never defined a feature called x subscript 0. In fact, this is just the value 1, meaning that we can just multiply it with theta 0, so as you can see it's the same as just writing theta 0. Why we do this will become clear in a second. But first, let's generalize this hypothesis for as many input features as we want. Remember that n is the amount of input features our dataset contains, so we can write the hypothesis as follows. Running up from x0 up until x subscript n. As n becomes large, this can become a very long expression. This will make it really unpractical to work with, and also when we implement this in software it will become very unpractical to work with if n becomes larger. That's why we will represent all these different multiplications as a vector multiplied with a vector that is transposed. We can write this vector multiplication as follows. Theta transpose times x, with x containing all the x values and theta containing all the theta parameters. They are both vectors that are element to the set R, n plus 1. In practice this means it has n plus 1 rows and 1 column. Or in other words, the vectors run from x subscript 0 and theta subscript 0 up until x subscript n and theta subscript n. Next we multiply this x vector with the transpose of the theta vector. When we take the transpose of this vector, we get this, which basically just gives you now 1 row and n plus 1 columns. If you don't understand or just need a refresher on vectors, the next video will explain the basic vector and matrix manipulations that you will need in this course. But in short, we can multiply these vectors like this. And as you see, it's exactly the same as our hypothesis. Now before we end this part, I want you to get a more natural feel of what the parameters theta stand for. Let's say we have this hypothesis, with x1 the amount of horsepower, x2 the age of the car and x3 the mileage of the car. We see that the hypothesis predicts that the base price of a car is $2,000, and for every additional horsepower, the price of the car goes up with some value. The age, on the other hand, will reduce the price of the car with some value, and also for every additional mile the car has, the price will also go down a little bit. That said, in the next video, we will see the basic vector and matrix manipulations we will need in this course. And it will become apparent that these vectors and matrices will have a very important aspect in the implementation of machine learning. Last video we extended our knowledge of linear regression to work with multiple features, also called multivariate linear regression. We simplified the notation of our hypothesis by working with vectors. So, in this video, we will give a quick recap about vectors and matrices, and we'll explain why there is another great benefit to working with matrices and vectors in real-world machine learning applications. So let's jump right in. First, let's understand what matrices and vectors are. Matrices are rectangular arrays of numbers, while vectors are one-dimensional arrays. We define the dimension of a matrix or vector as the number of rows times the number of columns, and we define it as follows: R, m by n, with m the amount of rows and n the amount of columns. So for these two, we can say, this matrix is element to the set R, 3 by 2. And this vector is element to the set R, 4 by 1. However, as a vector is an n by 1 matrix, and thus the amount of columns will always be equal to 1. We will just use this notation to denote a 4-dimensional vector. As you might have noticed, we will use capital letters to denote matrices, and we will use lowercase letters to denote vectors. If we now want to pick a specific element out the matrix, then we say, let's take the ij entry in the ith row and the jth column. If we translate this for every possible entry, we get this. So if we want to take this element, we denote it with a subscript 11. For vectors, this will just be y subscript I to take the ith element. As you see, the elements run from 1 up until n. So here we start at y subscript 1 up until y subscript n. This is called 1-indexed. However, if you remember from previous video, our hypothesis looked like this, with x subscript 0 and theta subscript 0. That's why in machine learning we mostly choose for 0-indexed vectors, where we, as the name suggests, start our indexing from 0 up until n1. Now, let's talk about basic vector and matrix operations. Let us start with the addition and subtraction. Adding and subtracting two vectors is fairly straightforward. The process involves combining the corresponding components of the vectors. Let's say you have two vectors, a and b, each with n components. The sum of vectors a and b, denoted as a plus b, is calculated by adding their corresponding components. Like for example this. And the difference of vectors a and b, denoted as a minus b, is calculated by subtracting the corresponding components. For example like this. Note that in order to add or subtract two vectors, they must have the same dimension, meaning they must have the same number of components. For matrices, on the other hand, the same rules apply. So in order to add or subtract two matrices, they also need to have the same dimensions. Let's assume we have these two matrices, A and B. Then we can add or subtract like this. We can look to an example where we add two matrices. In fact, we just add each a subscript I, j, element with each b subscript I, j element. Subtraction is done in the exact same manner. We can also do a scalar multiplication, which means multiplying with a single numerical value. So for example, we can multiply this vector with 5 and this matrix with 2. Multiplication of a vector or matrix by a scalar involves multiplying each element by that scalar. It is very straightforward. We just take each element in the vector or matrix and we multiply it with the scalar like this. Also for the matrix, you just multiply each element with the scalar. One powerful operation is multiplying a matrix by a vector. This operation combines the elements of the matrix and the vector to produce a new vector. The result is calculated by taking the dot product of each row of the matrix with the vector. What this concretely means is that we take the first element of the first row and multiply it with the first element of the vector. Then we take the second element of the first row and we multiply it with the second element of the vector, and so on until we did this for every element in the first row. Then we take the sum of all these different products, and this will be the value for the first element of the new vector. Then we do the exact same thing for the second row of the matrix. We again take each element of the second row and multiply it with the corresponding element in the vector. Then we add all these products and the outcome will be the value for the second element of the new vector. We keep on doing this for all rows in our matrix. It is worth mentioning that you can only multiply a matrix with a vector as the matrix contains as much columns as the vector contains elements. Or in other words, if the vector contains n elements, we can only multiply it with matrices that have n columns. A nice tool I always use to check if you can multiply a certain matrix with a certain vector is this one. You write down the dimensions of the matrix and vector. And if the inner two numbers match, then you can multiply them and the result will be something of dimensions of the outer two numbers. For example, if we look back at our example and we write down the dimensions, you see that these two numbers match and the result is something of these two dimensions. Now you might be wondering why we would want to multiply a matrix with a vector in machine learning. Well, let's look at it together. Let's assume you already trained a model that looks as follows. With theta 0 equal to 2000, theta 1 equal to 107 and x subscript 0 is always equal to 1 as we saw in last video. Now that we got the trained model, we want to test it. We want to see how it performs on new unseen data and see if it can perform accurate predictions. So you might give it a test dataset that contains test example. Notice that I just called this dataset the test set instead of the training set. That because we define the training set to be the dataset that is used to train the model on and to get the right parameters for our hypothesis. And once the model is trained, we can test it with new unseen data points that come from another dataset. This other dataset, we call the test set. In most applications we provide this dataset in a CSV file that we can read out with some programming language of choice. The file contains for every test example the input data x, which in this case is x subscript 0, which is always equal to 1. And x subscript 1, which is the amount of horsepower. So our objective now is to write some code that will give us the predictions of the price of the car, based on these new test examples. We can do this with a loop that might look somewhat like this. And as you see, this might become a long and unpractical expression. Now this is where vector matrix multiplication comes into play. We can just make a vector of theta and a matrix of all input data like this. Now this matrix contains in each row a different test example and in each column a different feature. With the first column being x subscript 0, which is always equal to 1, and in the second row we got x subscript 1, which is the amount of horsepower. The nice thing about this is that we can easily read this in our application like this from the file. And that we now just can write the entire solution with one line of code. Yes, I know, that's just awesome. Now the result of this vector matrix multiplication is another vector, which is the output value or y value. So in fact, the price of the car for each test example will be in every row of this vector. So the first row contains the first test example, the second row will contain the second test example, and so on. So to summarize, we get the benefit that we can write clean, understandable code in much fewer lines of code. But additionally, it might also be computational more efficient than using loops. A lot of programming languages have very optimized linear algebra libraries that can compute these multiplications very efficient. Before we move on, if you found this video helpful so far and want to learn everything about machine learning and AI, I would recommend subscribing to this channel. Also, don't forget to leave any questions in the comment section below. Now that we have seen matrix vector multiplication, let's discuss some matrix multiplication properties. Unlike addition, matrix multiplication is not commutative, meaning the order matters. We can immediately illustrate this with previous example. If we try to write theta times x and we look at the dimensions of the matrix and vector, we can easily see that this operation is not possible. So unlike with real number, you can't just swap places between the things you multiply. This will give a different result. Or in other words, matrix multiplications are not commutative. However, on the other hand, they are associative, meaning the grouping of matrices in multiplication does not affect the result. So you can first calculate matrix B times matrix C and then calculate the result of matrix A times this matrix. Or you can start with calculating matrix A times matrix B. Either way you will get the same result. Moving on to matrix multiplication, this operation is more intricate. When two matrices are multiplied, the element in the resulting matrix is found by taking the dot product of the corresponding row of the first matrix and column of the second matrix. Let's try this together. We first take the dot product of the first row of the first matrix with the first column of the second matrix. This will result in this expression, and if you calculate it, it will give 58. Next you do the same with the second row of the first matrix in the first column of the second matrix. Now you do the same but with the second column of the second matrix. As you see, the first column of B is responsible for the first column of C, and the second column of B is responsible for the second column of C. In fact, you can just look at it like you were multiplying a matrix with a vector, and thus seeing all columns of the second matrix as different vectors, and at the end concatenating all these resulting vectors to form the new matrix. Just as we did before, let's look at the practical use of matrix multiplication in machine learning. Let's assume that you have two hypotheses of which you want to test which one can make the most accurate predictions. Meaning that we again have a test set like we saw in the matrix vector multiplication example. If we now not only capture the parameters theta in a vector, but capture them of both hypotheses like this in a matrix, then we can do a matrix multiplication, which will give us another matrix that contains not only the predictions of the first hypothesis but also of the second hypothesis. Two crucial concepts in matrix algebra are the inverse and transpose. The inverse of a matrix, when multiplied by the original matrix, gives the identity matrix. With numbers, this means if you multiply 12 by the inverse of 12, which is 1 over 12, you get as answer 1. In matrices, if you multiply a square matrix with its inverse, you get the identity matrix. The identity matrix is denoted as I, and it is just looks like this, with 1 on the diagonal and 0 everywhere else. The identity matrix is one of the only exceptions on the non-commutative rule of matrix multiplication, meaning that B multiplied by I gives you the same as I multiplied with B, namely just the matrix B. A second exception on this non-commutative rule is if you multiply a square matrix, meaning it contains as much rows as columns with its inverse, given that the inverse of this matrix exists, then you get the identity matrix. Matrices that don't have an inverse are called singular or degenerate. On the other hand, we can also look to the transpose of a matrix. The transpose of a matrix is denoted by subscript T and is obtained by swapping the rows and columns of a matrix. For example, if we look at this matrix called A, then the transpose of this matrix is obtained by switching the rows and columns of the matrix. Or in other words, a subscript I, J is equal to a superscript T subscript J, I. I hope this video helped demystify these fundamental concepts of matrices and vectors. Welcome back. In this video, we'll start with a short recap of linear regression with multiple features, also called multivariate linear regression, and then we'll extend our knowledge of multiple features to gradient descent. So, at the end of this video you will have a generic gradient descent algorithm that is able to work with as many features as we desire. To recap, we saw that we can write a general hypothesis for linear regression that has n variables or features. We saw that we can rewrite this long expression in vector notation. More specifically, in theta transpose times x, with both theta and x being vectors of dimension n+1 and with x subscript 0 always being equal to 1. Now we will look at the cost function for multiple features. Actually, the only thing that changes when we extend the cost function from one variable to multiple variables is the hypothesis itself. The notation, however, stays completely the same, except that we now not call it j of theta 0 and theta 1, but we call it j of theta 0 up until theta n. Or we can express it just like j of theta, with theta being a collection of all theta parameters. Also, for gradient descent, we get a similar expression as the one from one variable. The only thing that changes is that we now use a cost function that is dependent on theta 0 up until theta n. And that we not only need to do a simultaneous update for theta 0 and theta 1 but also for all other parameters. In fact, the only thing that changes is the derivative part. Like we saw before, these are the two different derivative parts for respectively theta 0 and theta 1. But now that we work with multiple features, we can't write x superscript I anymore, as this will include more than one feature. Thus we must define it as x subscript 1, superscript I to define the first feature for the ith training example. If we extend this for more features, we notice that we get each time a fairly similar term. In fact, as we know that x subscript 0 is always equal to 1, we can add this over here, and now we really see the similarities between all these equations. In fact, we can now write one general gradient descent algorithm that works for both linear regression with one feature and with multiple features. So to summarize, we just created a general equation for the hypothesis, the cost function, and the gradient descent algorithm. Or in other words, n will define the amount of features we have and whether that is 1, for linear regression with one variable, or whether n is larger than 1, thus for multivariate linear regression. In both cases we can just use these general notations. Now that we understand the full gradient descent algorithm, how can we know for sure that the algorithm is working correctly? Well, that's what we'll see in this video. We'll learn you how you can check that your gradient descent algorithm is working correctly and how you can debug it efficiently. Let's jump straight in. The most used tool to check if gradient descent is working correctly is by printing the value of the cost function in function of the number of iterations of the algorithm. So let's assume that our initial theta values give us a value for the cost function that is relatively large compared to the minimum. If we assume a problem where we only need theta 1, let's say we start out over here. If we now execute the gradient descent algorithm one time, we end up with some lower value for the cost function. We now just keep on repeating the algorithm until we reach the minimum of the cost function. And every step we take, thus every repetition of the algorithm, we plot the value of the cost function in a graph. So after some time, we might see a graph that looks like this. Now here we only assumed that we work with theta 1, but we can also extend this idea to a cost function with multiple variables. Now we might end up with a graph like this one. And this graph can give us a lot of insights into the algorithm. First of all, we immediately see if something is wrong. Because we know that gradient descent is working correctly if the value of j decreases on every iteration. So if we see a graph like this or this, we immediately know something is not right. It can be that there is something wrong with your implementation of the gradient descent algorithm, but in most cases, this is the result of the learning rate being too large. If you want to know how we can choose the correct learning rate, then I recommend subscribing, as this will be the topic of next video. But first, let's get back to this graph. This graph is also very useful if the algorithm takes a lot of steps to converge. Because you don't know beforehand how many steps gradient descent will need to converge. In some cases it might be 100s, in other 1000s, and in some special cases it might run up to millions of iterations. So you don't want to wait for millions of iterations, only to see that there is something wrong with the algorithm. So what you can do is, you let the algorithm run for some time and plot its values in function of the amount of iterations. This way you can immediately see if it is working correctly. A second thing we can extract from this graph is that between 400 and 500 iterations, the value of the cost functions doesn't change a lot anymore. We can see that after 500 iterations the algorithm kind of converges. Of course we don't want to be estimating this from some plot. We want to implement this in software to know if the algorithm has converged. So we can check every iteration if the difference between the current value for j and the previous value for j is smaller than a certain threshold. This threshold is often denoted as tolerance or epsilon. If the change is smaller than this threshold, the algorithm is considered to have converged. The choice of the tolerance value depends on the specific problem, and it may require some experimentation to find a suitable value. Commonly used values for tolerance include 1 times 10 to the minus third and 1 times 10 to the minus sixth, but the appropriate threshold may vary based on the scale and nature of the objective function. A second method of checking if gradient descent is working correctly is to print the value of j and the value of the gradients and monitor its behavior. Some key points to look out for are: the value of j should decrease on every iteration. The gradients are becoming smaller as the algorithm progresses. Large gradients or sudden changes might indicate a problem. Keep an eye on the cost function and gradients for not a number or infinity values. These can occur due to issues such as overflow, underflow, or mathematical errors. By systematically going through these checks, you can often identify the source of issues in your gradient descent implementation. In this video, we'll explain how you can choose the best learning rate for your specific application. But first, do you remember what the learning rate was again? I recommend you pause the video for a second and think this through. The learning rate, also called alpha, basically tells us how big of a step the gradient descent algorithm takes. Concretely, we can explain this as follows. The larger alpha, the larger the step of the gradient descent algorithm. This gives as benefit that we might converge faster and in less steps. On the other side, if alpha is too large, we might never converge. And thus the gradient descent algorithm will fail to converge. Thus, the learning rate being too large might a reason that your gradient descent algorithm is not working correctly like we saw in the last video. So you might be thinking, okay, so we just take a very small value for alpha. Yes, for a sufficiently small learning rate, the value of j should always decrease on every iteration and we get a correct working algorithm. However, for a very small learning rate, the steps the algorithm will take will be very small. And thus the time until convergence can be very long. So it is important to find a good value for alpha that is neither too large nor too small. So let us now look how we can do this. But first, if you liked the video so far, please consider subscribing. Now we will learn how to choose a good learning rate. Finding the best learning rate for gradient descent in linear regression involves experimenting with different learning rates and selecting the one that converges quickly to the minimum of the cost function. Here's a simple method to determine the optimal learning rate. Start with a range of learning rates. It's often beneficial to explore a logarithmic scale since it can provide a good range for exploration. For example, 0.001, 0.01, 0.1, and 1. Next, implement the gradient descent algorithm for linear regression using each learning rate in your range. Choose a maximum amount of iterations you want to perform and run gradient descent. After each iteration, record the value of the cost function. Now you can plot the cost function against the number of iterations for each learning rate. Concretely, for our range of values, we get 4 plots, one for each learning rate in the range that we defined. They might look as follows. Now analyze these plots. If the learning rate is too small, convergence will be slow, and if it's too large, the algorithm may overshoot the minimum. Look out for the plot that converges to the minimum in the shortest number of iterations without oscillations or divergence. And voila! We now see that alpha equals to 0.1 gives us a good value for the learning rate. Keep in mind that this is a heuristic approach, and the optimal learning rate might depend on the specific dataset and problem. It's a good practice to experiment with different learning rates and monitor the convergence behavior to find the most suitable one for your particular scenario. Now that we have a general idea that the best learning rate for this specific problem will be around 0.1, we can even go one step further. We can now redefine our range. The idea is to narrow down the range and pinpoint the learning rate that results in the fastest convergence without overshooting or oscillating. For example, we can now take a range of 0.03, 0.06, 0.1, 0.2, and 0.3. If we now do steps 1 up until step 3 again, we might find that alpha equal to 0.2 gives an even better value for the learning rate. So, using this iterative process, we can try to pinpoint the optimal value of alpha for our specific problem. Now that we have a process to find a good value for the learning rate, let us look to some Python-like pseudocode to make things more clear. We start by defining a range of values that we want to try as our learning rate, and we set a max number of iterations. We also make a list that keeps track of the value of j when we perform gradient descent, because then we can lot the values of j in function of the number of iterations later on. Next, for each learning rate in the range, we perform gradient descent and record the cost after each iteration. Then finally, when we have done this for every learning rate, we can plot the cost in function of the amount of iterations for every learning rate and choose the learning rate that converges in the least amount of steps without oscillating or overshooting. So, now you know how to choose alpha. In this part, we will look at the concept of feature scaling. This will allow us to speed up gradient descent as illustrated in these two drawings, also called contour plots. To give a quick recap, these plots describe the value of j in function of θ1 and θ2, and every circle describes that on every point of that circle we get the same value for j. So for all the combinations of θ1 and θ2 that lay on that circle, we get the same value for j. If you want a more detailed recap of what these contour plots mean, I recommend that you pause the video and check out this video, which you can find on the channel. So basically, the more elliptical the contour plot, the longer convergence can take. And if we get a contour plot like the one on the right, convergence can be faster because gradient descent can take a more direct path to the minimum. So the goal of this video is to make sure we get a contour plot like illustrated on the right. Our first task is to understand why we might end up with such an elliptical contour plot. To fast forward, it's our dataset that describes how our contour plot will look like. To illustrate this, let's look at an example. Let's assume we want to predict the price of a car based on the mileage of a car and the age of a car. Then we get a hypothesis like this one, with x1 equal to the mileage and x2 equal to the age. Typically, x1 will have a large range of values, for example between 0 and 130,000, and x2 will have a small range of values, for example between 0 and 20. If we plot this dataset, it will look as follows. And if we now plot the cost in function of the parameters θ1 and θ2, also called the contour plot, we might see a figure like this one on the right. As you see, this is very elliptical. This is because a large range for a feature will typically result in a small range for the corresponding parameter, and a small range for a feature will typically result in a large range for the corresponding parameter. This can be illustrated by following example. If we look how the real hypothesis of this example would look, the hypothesis will subtract some value for each additional mile the car has. So if you assume that the car has a value of x1 equal to 130,000 and you would multiply it with a parameter θ1 that is equal to 5, you would subtract more than $500,000 from the value of the car. That's way too much. So it's easy to see that θ1 must be relatively small to be accurate. The same can be said for the age of the car, x2. Because the age is relatively small, let's say we have a training example where x2 is equal to 10, and if you assume that θ2 is equal to 5, you would only subtract $50 from the price of the car. That's way too low, so we see that θ2 should be a relatively large value. So, to recap, a big difference in ranges of the features results in a big difference in ranges of the parameters and thus in an elliptical contour plot. So what we want to do is to make sure the features are in a same range of values. One way to do this is to divide the features by the largest value of that feature in our training set. For example, the largest mileage that occurs in our training set is 130,000 and the smallest mileage is 1,000. Also, the largest age is 20 and the smallest age is 0. Then we get the following ranges. Now you should scale x1 and x2 as follows. You divide them by the largest value of that feature that occurs in the training set. This way we will get a dataset that has features in a similar range, and thus we will get a dataset that might look like this. Now the contour plot will look more like a circle, and thus gradient descent can converge faster. A second method to scale our features is by applying mean normalization. This is done by taking all values of a specific feature, computing the mean and range of this feature, and then you apply following scaling technique to all the values of that feature. For example, let's assume that the mean of x1 is 40,000 and the range is basically the largest value that occurs minus the smallest value that occurs. So in our case we have a range of 129,000. Now we apply this scaling transformation to every value of x1 and we end up with all values of x1 between these two values. Now we can apply the same logic to all other features. Then we end up with all features being in a similar kind of range. For example, we can do the same for the age of the car. You might notice that the ranges of the features are not exactly the same. That's true, but this is no problem. As long as the ranges are not too far from each other, you still obtain a fast gradient descent algorithm. You should aim to get our features between -1 and 1. However, this isn't a strict rule. If our features are a little bit bigger or smaller than this range, this will be no problem. However, try to stay close to this range. For example, if we have a feature x1 that is between 0 and 3, this is fine. If we have a feature x2 that is between -3 and 1, that is fine. However, if we have a feature x3 that is between 0 and 50, this is not fine and you should rescale this feature. Also, if you have a feature x4 that is between -0.004 and 0.3, this is not fine. You should also rescale this feature. So as long as the feature have a range that is close enough to each other, it's fine. You shouldn't worry if your features are not exactly between -1 and 1. So to get back to mean normalization. If we now plot the scaled dataset again, we might get a figure that looks as follows. As you see, all data will now be centered around 0. This will give us a contour plot that's less elliptical and thus gradient descent can converge quicker. Now, you might be wondering, okay, that's great, but what do we do after we scaled our features? That's a good question. Therefore, let us now look at a step-by-step guide on how we could scale our features. But first, if you liked the video so far, please consider subscribing. So, you are working on a problem and you notice that your different features have very different ranges. Then a first step consists of scaling our features so that they are on a similar range. One example to do so is by applying mean normalization. If you did this for your original dataset, you get a new dataset containing the scaled features. Next, you train your model on the scaled features. After training, you obtain your parameters theta that are trained on the scaled dataset. Now you are able to make predictions on new, unseen data. However, if you do this, you also need to transform this new unseen data with the same scaling transformation as you did on the training data. And finally, if you want to interpret the model's predictions in terms of the original scale, you should invert the scaling transformation. This is done by applying the scaling in the reverse order, just like this. We have seen that gradient descent can help us to find the best fitting parameters theta. However, from the contour plot, we can see that depending on where we start from, we can converge faster or slower to the minimum. So concretely, our initial theta values will dictate where we start from and thus how long convergence can take. So with what values should we initialize theta? Should we just set them all to 0 at the beginning, or is there a better value to initialize them with? That's what we'll find out right now. Initializing parameters in machine learning is an important step that can impact the performance of your algorithm. While initializing parameters with 0 is a common practice in some algorithms, it's generally not recommended for linear regression. When you initialize all parameters, theta, with zeros in linear regression, the update steps during gradient descent will be the same for all features, and they will all converge to the same value. This can lead to slower convergence and suboptimal results. So how do we initialize them? In linear regression, where you have a simple linear relationship between input features and output, initializing parameters is relatively straightforward. Since the objective in linear regression is to find the weights that minimize the mean squared error or a similar loss function, you can often use simple strategies for parameter initialization. A common practice is to initialize the parameters randomly. This helps break the symmetry and ensures that each parameter starts with a different value, allowing the algorithm to learn more effectively. You can initialize the parameters with small random values or draw them from a normal distribution. Here's a simple example using Python and NumPy to initialize weights for linear regression. In this example, NP random RANDN generates random values from a standard normal distribution. You can experiment with different initialization methods, but random initialization is a good starting point for linear regression. By multiplying the random values by 0.01, you ensure that the initial parameter values are on a smaller scale, which can lead to more stable training. This is particularly important when using activation functions like sigmoid or tanh in neural networks, where keeping the values in a specific range can help prevent issues like vanishing, exploding gradients. In linear regression, it might not be as critical, but it's still a good practice for consistency and to prevent potential numerical instability. Let's assume we have now 3 features with each feature 5 training examples. This means that we need to initialize 4 theta values, namely theta 0, also called the bias, which corresponds to this feature x0 that is always 1, remember, and the other 3 theta values. So if we now run the code, we see that we get 4 small randomly distributed values for theta. It's worth mentioning that for simple linear regression, the initialization strategy may not have a significant impact because the optimization problem is convex, and you can often find a global minimum regardless of the initial parameter values. However, for more complex models, especially neural networks with multiple layers, the optimization landscape becomes more non-convex. In these scenarios, the choice of initialization can significantly affect the convergence and training efficiency. In those cases, initialization methods like Xavier, Glorot, or He initialization, which are designed to address challenges in deep neural networks, might be more suitable. These are techniques we will see later after we have seen neural networks. So far, we've only been using a straight line to fit the data. So does that mean we could only use straight lines for a hypothesis? Well, the answer is no. It's time to buckle up because things are about to get curvy. Now, take a look at this dataset. It's clear that a straight line won't cut it here. It's like trying to fit a square peg into a round hole. We need something more flexible. So we would like to end up with a hypothesis that looks more like this. This is what we call polynomial regression. Here we embrace higher-order features to capture the intricacies of our data. For example, we could try to fit a quadratic function through the training set. But if we look closer to this, the price of the car would go down again if the amount of horsepower goes up even further. So maybe we could even look at a third-order polynomial. For example, like this one. As you see, this fits the training data way better and it will result in more accurate predictions once the model is trained. But wait, how do we go about fitting a polynomial model through this wavy data? It's actually not that difficult. We can do this through the machinery of multivariate regression. For example, if we assume we need this third-order polynomial to fit the data, then we can just map the higher-order terms of the feature x into the features x1, x2, and x3. Now we get this hypothesis that is familiar to us. We can just use it as we did before. So we can train the parameters as we did before using gradient descent, resulting in the parameters theta that fit best through the data. After our parameters are trained, we have a model that can make predictions on new unseen input data. But here's the plot twist. In the case of polynomial regression, feature scaling becomes really important. It's not too hard to see that our ranges of the different features are very different. Assume that x1 has values between 20 and 1000, then x2 has values between 400 and 1 million and x3 has values between 8,000 and 1 billion. If you forgot how you could scale your features or you haven't watched this video yet, I recommend that you check out this video on the channel. Now, brace yourself for a mind-blowing move. Square roots. Yup, you heard it right. We can even take the square root of our features and fit them through the data. It's like adding another layer of sophistication to our model. And guess what? We're not even limited to the features handed to us on a silver platter. We can create our own features, molding models as complex as our hearts desire. It's like being the architect of your own data universe. For example, assume you want to predict something based on the length, the depth, and the height of a house. We know that we could multiply these parts to obtain the volume of the house, meaning that it is just as valid to make your own feature X, which is the volume of the house. This gives us following hypothesis, and if we train it, it might even be a better model than if we would have trained the original hypothesis with the 3 different features. However, this is not always the case. This is up to you to test both models and see for yourself. Now, I get it. This might sound very overwhelming. Which features should I take? There are so many different possibilities. Don't worry, though. Soon, we'll unravel algorithms that choose the right features for you. It's like having a personal assistant for your machine learning endeavors. So, stick around because the journey is just getting started. Do you remember gradient descent? The algorithm that could get us the optimal value for the parameters theta. Well, there's actually another method to get this job done. But first, to recap, gradient descent iteratively updates the parameters so that every iteration we decrease the value of j. We keep on repeating this until we reach convergence, or in other words, until we end up close enough to the minimum of the cost function. And the values for theta that we now have at convergence are the optimized values that we will use to make our model. Now, what is this mysterious second method? Well, just as gradient descent, we can use it to optimize our parameters theta. However, instead of gradually getting better values for theta, this new method will calculate the optimal values for theta in just one step. So it's a way of analytically calculating the optimal parameter value. To get intuition in how this method works, let us look at an example where we just have one parameter theta1. Do you remember what it means if we have only one parameter? Well, it means we will train a model based on just one feature, for example, only using the amount of horsepower to estimate the price of a car. That said, the new method for finding the optimal parameters is called the normal equation method. And what it basically does, it calculates in just one step the optimal values. If you remember well, the optimal values for theta are found when we end up in the minimum of the cost function. And what indicates that we are at the minimum? Yes, you guessed right. It's the point where all partial derivatives of the cost function are 0. So the normal equation method lets us go immediately from our initial values to the optimal values, and these partial derivatives equal to 0 is the key to it all. What the normal equation does, it sets all the partial derivatives equal to 0 and then it solves for theta. It's actually just a bunch of matrix operations, and we are not going into detail of how it works. We'll just show you how you can use it in your machine learning applications. Mathematically, it can be proven that we can solve for the optimal parameters by calculating following term. We need to multiply the matrix that contains the input features with the same matrix that is transposed. Then we take the inverse of this new matrix and we then multiply it with the transpose of the input matrix again. And finally, we multiply it with y, which is the vector that contains the labels of the training data. Let us look to an example. From this dataset we get the following input matrix x and following output vector y. That's actually all we need to solve for theta. You can now implement this in the programming language of your choice. In Python, this might look like this. Alright, so here's the code we'll be breaking down. It's a Python script that calculates the optimal parameters, theta, for a linear regression model using the normal equation. Let's go through it step by step. Let's start with the normal underscore equation function. This is where the magic happens. The function takes in two parameters, x, which is our input matrix, already including the bias term, and y, which represents the labels. The function calculates the optimal parameters using the normal equation formula. Now, Let's take a look at our example data. We have an input matrix X with 3 rows and 2 columns, representing one feature and the bias term for 3 training examples. We also have a label vector Y with 3 labels to the 3 training examples. Finally, we print out the optimal parameters, theta, that we've just calculated using the normal equation. So we can now execute this code and we will get the optimal values for the parameters. That said, let us now look at some differences between the normal equation method and gradient descent so that we can find out when we should use which method. First of all, with gradient descent we need to find a good value for the learning rate alpha. With the normal equation method, we don't need to find a good value for alpha, so that's one thing less to think about. Next, with gradient descent we need to scale our feature when the ranges of different feature are far apart. With the normal equation we don't need to do that. That's another thing less to worry about. So far only benefits to the normal equation method. The downside of the normal equation method lays in the amount of features it can handle. If the amount of features n becomes very large, let's say over 1,000, then the normal equation becomes very slow. This is because the inversion of a matrix is very costly. It takes a lot of time to invert a matrix that is large. We know that this term gives us an n by n matrix. So inverting this matrix roughly has a cost of n to the third. On the other hand, gradient descent works well even when we have a lot of features. Gradient descent works even well if we have 1,000,000 features. And finally, the normal equation doesn't work for more complex learning algorithms like logistic regression. So we can't forget about gradient descent. The gradient descent algorithm still stays very relevant in machine learning. So now that you have a new method to solve theta, I suggest you try it out, and if you have any questions, feel free to ask them in the comment section below.